So last week I left off at page 58 and 59. Yeah? I left off by showing you frog legs that can twitch if I were to throw salt to it. Remember? But don't go to the fish market or the wet market and start sprinkling salt every week. So obviously,
I'm preserving it. I'm preserving it. I'm not preserving it.
Why? Oh yeah. Okay, fair enough. If it's fresh, actually it will still make chocolate. Oh, true. Yeah, it was preserved already. Okay, so last week, this is how far we've come up. So we've learned when we look at our periodic table. Where is the exact case? Okay, so far we've learned this non-metals. Sorry, if you have metals and non-metals, you can end up forming, you all tell me, hope by now you know what kind of ions they form. Metals tend to form what kind of ions? Okay, thank you. The meow one, the 10 ions. Okay? Because they tend to lose electrons. Whereas non-metals tend to want to gain electrons. So you end up getting onions. They are very sad, make you cry. But if you have cations and anions together, they can form a special kind of bond that we refer to as, thank you, ionic bond. Ionic bonds are held together by, oh thank you, electrostatic forces of attraction. Because the plus and the minus are electrically attracted to each other. Ionic bonds result in ionic compounds. And last week, we learned about the properties of ionic compounds. So, what are the 4 physical properties of ionic compounds we learned last week? Okay, let's do it. One of them, it is hard and brittle. We learned that it's hard and brittle because if you apply enough force, if the ions align in a way that they repel each other, they will end up fracturing and breaking. What page are they? 58 and 59. Okay, so I'm revising the 4 physical characteristics of ionic compounds. Xavier? Thank you. Okay, Xavier says they are soluble. I don't remember where this is. I think it's point number 2. 3. Thank you. So it is soluble. Point number 3. Doesn't matter. I'm just trying to follow the textbook in case some of you get lost. Zen?
It conducts electricity.
Okay, thank you. Zen says it conducts electricity. But then the next point we will always ask is conduct electricity in what state? Okay, good. Liquid or dissolved. Another way to say liquid state will be molten because it's melted, or dissolved state. If you look at a textbook, they will also write another way of describing dissolved is to write this word A-Q-U-E-U. Oh, I don't know how to spell it. What do you spell it out? A-Q-O. Okay, there's one more U. Okay, aqueous. This is how you pronounce it, aqueous. Aqueous means to be dissolved. So if someone were to say aqueous sodium chloride, it means dissolved sodium chloride. And then the next question people always ask then, how come in solid state cannot conduct, but in molten and dissolved can? Okay, not the water have to join the particles. It has to do with the ions. How do the ions, what's the position of the ions in solid state versus when it's melted and dissolved? There's a difference. Okay, nothing to do with the space. To conduct electricity, you need. Okay, yes, Dee?
The electric structure is broken down so that the ions can move around, so they become mobile charge carriers.
Okay, wow, that's a very wholesome answer. Karthik, you want to add on anything? Okay, Xavier? Okay, then, okay, so this one is the one we aspire towards. Xavier helps the layman understand the moving. Yeah? Because in a solid state, the ions are all fixed in place. All cannot move. Oh, they are moving but vibrating on the spot in fixed positions. But when melted, all of them are now free to move. They can slide over each other for all I care. Okay? But it's this movement that allows us to conduct electricity. So the keyword you want to make use of, in your textbook you should highlight it by now. The word should be mobile charge carriers. Mobile means, hey, sorry, I know this mobile charge carrier sounds like a handphone kind of thing. No. So mobile means can move, not your handphone mobile. Charge means can carry electricity. Carriers means can carry. So only in molten and dissolved state can the ions behave as mobile charge carriers. I say again, in dissolved and melted state, the ions become mobile charge carriers. They can move and they can carry electricity. That's where we left off last week. You cannot find mobile charge carriers in your textbook. It's on page 59, paragraph 2. The ions. When the ions can move, we say that they become mobile charge carriers. Hey, sorry, I missed out. Then there's one more physical characteristic. Yeah? High melting and boiling point. Why is the melting point so high? Why the boiling point so high? Because really, yes, it's down to this. The electrostatic force of attraction between the ions is very strong. So it takes a lot of energy to be able to melt or boil them. Yes? Cut them what? Oh, Sivas, we physically break the bonds. In a sense, when you are talking about brittleness, when you give it a press, you are sort of breaking the electrostatic forces of attraction. That's why they shift positions and they end up repelling. So technically it could be physical force. Oh, that will generate. Okay, so that's where we left off last week. This week, we're going to focus our attention on what about non-metals and non-metals. Okay, when we look at non-metals and non-metals, the bond we are looking at is not ionic in nature. Okay, have I done this? Okay, I think I've gone through that you found covalent, but we have not talked about the properties of covalent. Yeah? Okay, so today we're going to focus on that. What happens if we have covalent bonds? Yeah, thank you. Rather than lose or gain, the idea here is that we share. We share electrons. And our focus for today is to look at the physical properties. What is the physical properties of elements that come together via covalent bonding? That's our scope for today. No, not the opposite. Okay, so where am I today? I'm on page 62, 63, and 64. That's our scope for today. 62, 63, and 64. What are the physical properties of covalent substances? Yeah. Okay. We are going to highlight bullet points A and B now on page 62. Okay, on page 62, we are going to highlight bullet points A and B now. Yeah, the headings, page 62. These are the two kinds of covalent substances you will encounter. Page 62, and you highlight point A and B. Covalent substance with simple molecular structure, covalent substance with giant lattice structure. These are the two kinds of structures we're going to look at today. Anyone still remember what is the structure that ionic compounds have? Okay, yeah, it's a long word, right? It is
Giant lattice.
giant, ionic, lattice.
Letter structure.
Okay, thank you. Structure. Not lattice, huh? So you are 10 years down the road, I will be able to recognize this class based on how you pronounce things. Or we at a scientific conference, yeah, here's what I say onion, cashews, lattice, structure.
GN, ionic, lattice, structure.
Okay? For covalent substances, there are two kinds of structures. One kind of structure is the same as the ionic kind. So we also call it giant, but not ionic, covalent. So if you look at point B, it says giant, covalent, lattice, structure. Okay, so that is the first one. Very similar to ionic. Second kind of structure you may find covalent substances have is of the simple molecular kind. Simple molecular. And actually we've learned quite a number of simple covalent substances with simple molecular structure. Let me give you a few right now. For example, remember CO2, H2O, hydrogen, oxygen, nitrogen. These are all simple molecular structures. So actually include the word structure here. Now examples of covalent substances that have giant covalent lattice structure is, give you one, diamond. Diamond is made up of carbon, lots of carbon joined together. Graphite is another example. You know your pencil lead? Yeah, it's made of carbon. Okay, then a lot of you are saying silicon. So it's all your textbook, silicon dioxide, so on and so forth. Okay, that is our scope for today. We're going to look at these different kinds of structures. Yes? How come? You're asking what? Okay, so it's your question what leads them to decide whether it's diamond or okay. I think it's the conditions through which it was formed. For diamond, you require very high pressure and temperature for the carbons to end up bonding in this way. You actually can make diamond from, you can make artificial diamonds from just carbon. You can even possibly convert this to this with the right conditions. Pressure and okay, so that's where we are today. We're going to learn about the physical properties of these two kinds of structures. So you'll find all the physical properties on page 63 as well as 64 of your textbook. Okay, so I'm going to go on. Yeah. Oh, why do you say trees are diamonds? No lah. Carbon got many ways of joining with each other. So trees contain carbon, but they don't contain carbon in its purest sense and join this way. And the carbon in trees are joined to form sugars. So you don't find carbon in this form. Okay, so we're going to learn about covalent substances today. I'd like you to take note of, and maybe perhaps compare it to ionic substances. Right, when you look at ionic substances, we know they have high melting boiling point, can conduct electricity, is soluble, is hard and brittle. Are there some similarities or differences when we look at these two structures and their properties? Okay, that's our scope for today. Yes, are you ready? Okay, let's go.
Covalent bonds. In this video, you're going to learn about covalent bonds, how they're made, and how they form. If If you haven't seen it already, first have a look at our video, Structure and Bonding. Only the noble gases exist naturally as single atoms. All the other elements of the periodic table have partially filled valence shells, or outer electron shells. Atoms bond by swapping or sharing electrons in their outer shells. When very different atoms react, like metals and nonmetals, they normally swap electrons. This is ionic bonding. But when similar atoms react, like nonmetals combining with other nonmetals, they share electrons. This is covalent bonding. Nonmetals are found on the right-hand side and upper part of the periodic table. Some common nonmetals are carbon, nitrogen, oxygen, and the halides. They have shells of electrons that are normally half or more than half full of electrons. Since they have a strong attraction for a few additional electrons, it is energetically unfavourable for them to lose electrons, so they share electrons by overlapping orbitals. This makes a bonding orbital, or covalent bond, that contains two electrons. If there is space in the outer shell, a non-metal atom can form double or triple bonds, like in oxygen or nitrogen.
It's all recap from last
In the
week.
displayed formula of a compound, we represent a covalent bond with a straight line, like this. We can also represent a covalent bond as a dot and cross diagram. These diagrams show only the valence electrons. To learn more about dot and cross diagrams, watch our video on dot and cross diagrams. Covalent bonds are directional, which means they are in a fixed position, like holding hands. This is different from ionic bonds, which are formed with an electrostatic attraction between charged ions. The overlap between orbitals means that the atoms in covalent bonds are very close. These things make covalent bonds strong. There are two kinds of covalent structure: small molecules, like water, and giant compounds, like diamond. Because the electrons in the bonds are evenly shared, bonds are not polarized. There is little attraction between molecules, and forces between molecules are weak. Compounds made from small covalent molecules have low melting and boiling points and are volatile. They also don't conduct electricity. Carbon and soot are low melting and boiling.
So this is the first kind of structure. When we look at things like water, CO2, H2O, and O2, they exist as molecules by themselves. So for example, if I look at H2O, here I have the oxygen, I have two hydrogens, and they exist like that. There can be other water molecules near it. But these water molecules are not covalently joined together. They are separate molecules. That's why we say it's simple, and that's why we say it's molecular, because this is their structure. Just three atoms joined together. For H2, just two atoms joined together. But take note, between the water molecules, there is some very weak attractive force. So between, there is weak and what we call intermolecular. Okay, inter means between, molecular that means between molecules, forces of attraction. So between the molecules, there's some attraction, but very, very, very weak. So where's the covalent bond? You find the covalent bond within the molecules. So for example, if I were to zoom into one of these water molecules, let's zoom in big. So here I have a oxygen, and here I have a hydrogen. Where's the covalent bond? The covalent bond is between the hydrogen and the oxygen. This is the covalent bond. Okay, did I do it wrongly? H2O, so two hydrogens, one oxygen. Yeah? So you find the covalent bonds between the atoms. Not this red one here. This red one is just very weak forces of attraction between them. But within each molecule, this covalent bond is actually really strong. Is that it? Sorry? Yeah, then that's a good question, right? This, I say if this is weak, then what does it look like solid state? So actually we did encounter the simulation before. Okay, I'm going to go back to states of matter. So we go to states of matter, I'm going to look at water. Okay, so look at water. Can you see all the little Mickey Mouse? Yeah, this is a simple molecular structure. You find that all of the compounds, they exist as little molecules. But they are, each molecule is still attracted to each other. Just different strength at different states. For example, at solid state, you find that the intermolecular force of attraction is stronger, so they are closer to each other. At liquid state, the intermolecular force of attraction is slightly weaker, so now they can slide over each other. At gas state, the intermolecular force of attraction is very weak, so now they are very far apart. But one thing has not changed between all the states. Between solid, liquid, and gaseous state, one thing has not changed. The covalent bond. Water is still water. Notice in solid, liquid, or gas state, this bond did not break at all. They still exist as water. The only thing that changed is what is here, in between the water molecules. The stronger the force, the closer the water molecules will be together. They will be solid state. Another example we can look at is, for example, oxygen. Look at oxygen in its solid state. Can you see that there are lots of tiny oxygen molecules? Two oxygen joined together. If you go to the liquid state, the force of attraction between the oxygen molecules are weaker. Gaseous state, even more weaker. However, one thing has not changed. The bond between the oxygen. So if I were to zoom in into this oxygen over here, oxygen bond with oxygen, this covalent bond over here did not change. It is very strong. You cannot break oxygen just by changing temperature. But what changed? The force of attraction between the oxygen molecules. It is that force of attraction that changes the state of the matter. Not sure if I confused you there. Okay? Yeah, so you notice nothing changed in the covalent bond. Only the force of attraction between each molecule that changes. That's classic of a simple molecular structure. Yes, Ed? Oh, so you have a drop of water, you split into two parts. So, okay, so what's your question? Oh, okay. I mean, you have experienced before, right? If you have a drop of water, technically if you want to, you could split the droplet into droplets, right? What you have just observed there is that you kind of split the force of attraction, but within each droplet, they still have force of attraction. That's why they clump together as one water droplet. If you bring the water droplets closer together, they could end up clumping again because the force of attraction will attract each other also. Okay, what are some of the physical properties of simple molecular structures? Let's look at page 63 of the textbook. So I'd like you to highlight some of the points. When you look at simple molecular structure, number one, the melting and boiling point is very low. Melting point, boiling point is low. So that's one of the first things you can highlight. I believe that is 1A. Usually low for covalent substances with simple molecular structure. Because the force of attraction between the molecules are very weak. Second, it usually cannot conduct electricity. Regardless of solid, liquid, or gaseous state, cannot conduct electricity. If you look look at my screen, water, whether it's solid, liquid, or gas, you do not see ions. You do not see mobile charge carriers. They can move, but they are not charged, so they will not be able to carry electricity. Last but not least, when you look at covalent compounds, they tend to be insoluble in water. Cannot dissolve in water usually. But they are pretty good at dissolving in your textbook they write organic solvents. So you look at bullet point number 3, they say they are usually insoluble in water, but many of them are soluble in organic solvents. What are organic solvents? Okay, I'll give you an example of organic solvent. Oil. Oil is an example of organic solvent. Covalent compounds tend to dissolve better in such solvents. They tend not to dissolve very well in water. Sorry? Ethanol. Okay, good question. Ethanol. Is that an example of an organic solvent? I do not think ethanol is an example of an organic solvent. Okay, so 3 properties I'd like you to take note of for simple molecular structure. Low melting boiling point, because this force of attraction between the molecules are quite weak. They cannot conduct electricity in any state, because you look at all the states of the matter, there's no charge. Last but not least, these cannot dissolve in water very well. Yes? Physical state means, physical state means solid liquid. Do not. Okay. So here is a question. You look at point 1, bullet point A. The last part of bullet point A says, do take note that the covalent bonding between atoms in the molecule of these substances is not overcome during a change in physical state. What are they trying to say? They are saying this. Whether it is solid, liquid, or gas, the covalent bond inside the oxygen molecule did not change. That's what it's saying. Regardless of state, the covalent bond will not change. Yeah, answer the question. Oh, okay. Yeah. Okay, I take a short pause for you to consolidate your notes, whatever you just learned, before I go into the second kind of structural covalent substances can have. And you'll find that the other form of covalent substance, in some sense similar to the ionic giant lattice structure. Okay, then once we're done with this giant one, we will play a couple. Sorry? Oh no, once we're done with giant, we are going to play a Kahoot on all the kinds of bonds. Okay? All the kinds of physical structure. Yeah, open book. Yeah. Yeah, then the very last one is metallic bonding. Isabel?
That time you mentioned like elements and covalent compounds. Like what? Like
What's the difference?
yeah, and is it like the same?
So, so covalent elements, H2 and O2, they can have simple molecular structure. The compounds, covalent compounds, also can have simple molecular structure. So that's what I'm saying. Okay, I see good practice. Some of you have physical notes, they are consolidating your learning. Some of you have digital mind maps, they just keep changing every lesson. You add more branches. Yeah. You all need a slide? Okay, long. Okay, so last part before we play a quick Kahoot. There is another way non-metals can join with each other. Another form of structure they can form. Aside from simple molecules, they can join together somewhat like ions in a very large endless structure. That is the next part of our lesson. Let's have a look at how some elements, non-metal elements, are able to form these giant structures. Ready? Okay, so now I am between page 63 and 64, more so on page 64. Okay, more so on page 64. Because diamond and graphite are examples of non-metals that form these giant covalent structures. Yeah, last topic. We are done with syllabus. Yeah. Yeah. Okay. I want to give you all as much time as possible for revision. Yeah. If I have time today, I'll finish part until 11, right? Yeah. I hope to finish metallic bond even today. Then that means tomorrow onwards we can start our revision. What Chinese? Oh. Okay, let's look at the alternative form of covalent substance structure. Okay, ready? Okay, let's go.
In this video, we're going to learn about the different types of giant chemical structures and link these to their properties. There are three main types of giant chemical structures. Sand, graphite and diamond are examples of giant chemical structures.
So these are real life examples that you can find. One of them you cannot afford, but the other two you can. Yeah? Sand, graphite and diamond. They are actually covalent substances.
The arrangements of the atoms can be quite different. Sand contains silicon atoms covalently bonded to oxygen atoms.
So this is a compound, it's a covalent compound. Yeah. I expect you to know the two case studies, diamond and graphite. Okay, these are the two I expect you to know, diamond and graphite. I want you to know their properties of diamond and graphite. Because even though both have a giant lattice structure, they have slightly different properties. Okay, so there's sand. Sand is one example.
Four oxygen atoms are bonded in a tetrahedral arrangement around each silicon atom. Diamond has a very around each silicon atom.
And take note, this is just one part of the lattice structure. It goes on endlessly, okay, to form your small little sand crystals. How many corners are there? Yeah, so imagine this same way of bonding, but across, they go up, you go to the left, to the right, go down also. Yeah, that forms your sand grains. Next,
Diamond
diamond.
is a very similar structure, where all of the carbon atoms are joined by covalent bonds in a tetrahedral arrangement seen here.
So I have a question for you. Is diamond a covalent compound or is it an element? I ask again, is diamond a covalent compound or is it an element? Okay, then what's the definition of a compound? Compounds are made up of more than one type of element. Element just has one element. So look at diamond. Diamond is purely made up of.
Diamond has a very similar structure, where all of the carbon atoms are joined by covalent bonds in a tetrahedral arrangement seen here.
So this is purely made up of carbon. Therefore, this is an element. Okay? But this here, sand, is a compound because it's made up of two different kinds of elements. But what's the learning point here? Actually, for non-metals, you can have elements and compounds that both make use of covalent bonds. Here I have elements, and they make use of covalent bonds to stay with each other. Here I have compounds, they also make use of covalent bonds to attract each other. Yes?
Why don't you just call diamond?
Oh, why don't we just call diamond carbon? It's just marketing. And you could go into a jewelry store and say, I want this carbon. Yeah, then nobody will want it anymore. Here, I don't know why people want diamond. Diamond is just carbon. It's made of the same things that your pencil lead is made up of. It blows my mind. Yeah? Do you know that diamond does not come out in that shape there? So you see this plastic shape, right? Okay, as a child, right, I used to think that if you go into the mine, right, you go and bang, 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 right, then after that, you'll find this shape come out, you know? Yeah. People do not find diamonds looking like that. What is it? Diamond digger? Oh, gold digger. Okay, but as a child, I used to think that you find diamonds like that. But it's not, you know. Yeah, you know raw diamond what they look like? Yeah, it just looks like glass. Okay, I'll show you what diamond looks like for reals. A raw diamond just looks like a block of sugar. Or look like glass. Okay, sorry, yes? Exactly right. Don't know. Actually, to an untrained eye, you won't even know whether what you have in your hand is glass or plastic. Yeah? So, then how do they get from this to the classic shapes? Actually, what they do is that they foul it. They go and foul it until it has all those shapes. So it's artificial, and all the shapes and angles you see is man-made. Real diamond just looks like a transparent block. Geodes are also another kind of covalent compounds. Yeah? Hey, don't you think this is more pretty? Like you want to propose to someone, I thought this will look prettier, right? When you propose in one glass block. No lah, hey, we're going off topic, I don't know why. I proposed to my wife, okay, I'm severely going off topic. Okay, can't tell you how I propose, so let's go off topic. So my wife and I actually, I didn't give her diamond. What did I give her? I gave her metal. So I just give her metal. So, because my wife and I always thought diamonds are a waste of money. Because one diamond can cost thousands and thousands of dollars to use it for our honeymoon. So I didn't spend on diamond. Instead, I went to a metal smith. Metal smiths are where they teach you how to mold metal. So I went to a metal smith, then I forged my own ring. More romantic, right? So I melted metal, then after that I forged it, then I made my own ring. So this ring over here is handmade, customized, only one in the world, my wife and I. So I use this to propose to my wife. Then on wedding day,
You use the marker to propose.
okay, so then on wedding day, actually we didn't even get a new ring. We didn't even have a wedding. So we just went to the place where we have to sign our papers. Then they asked us to say our vows. So after we say our vows already, they say we can present the ring to each other. Then after that, I was like, hey, but we don't have it. We only have the proposal ring. So the both of us took off our ring. Then we put the pillow in front of them. Then after that, we took it back and then we put it there. Save money, So
Why you go for it?
it was COVID. Okay, listen. But why I share all this? Because diamond is worthless. Yeah, diamond is just made of carbon. Yeah? So, ladies here and guys, if you all can convince your partner not to buy diamonds, convince. Waste of money. Yes, then? Okay. My wife gave me wrong ring size. So when I put the ring on her, immediately it slipped off. So we went back to the metal smith, then we reforged sharing together. No, so you listen to me carefully. Diamonds are this shape because man decided. Okay, why did human decide to create all diamonds this shape? Why did they found this shape? Because it is in this shape that the light refracts the most. You know, we learn about refraction. Sorry, not refraction, reflection. It is in this shape that light reflects the most. That's why diamonds are so shiny. Just need to shine a little bit of light in, it will reflect so many times and make it look like it's glowing. Yeah, so that's why they call it this way. If you don't call it this way, it's not going to shine. Okay, sorry, I go severely off topic. Yes, Karthik?
How can like diamond and graphite is the same, I mean, diamond is like transparent, translucent, graphite is...
Okay, good question. So let's look at how it is bonded differently, covalently. That's why it results in different structures. Okay? So carbon is another one. Second case study I expect you to know.
Here.
Last one I expect you to know is graphite. What's in your pencil
For
left?
graphite, the carbon atoms are arranged in hexagonal sheets and have intermolecular forces holding these sheets together.
Graphite is a bit different. They form giant covalent lattice structures, but not in a large sense of the word. They form into sheets. So you see, there's one sheet on top, there's one in the middle, one below. All of those are giant structures, but they giant flat structures. But each giant flat structures are attracted to each other with intermolecular force of attraction, so that the sheets don't just fall apart.
These layers form a way when our pencils make a mark on paper, because the forces holding the layers together are intermolecular.
And that's why you can write with pencil lead. Because every time you put a pencil lead on paper and you apply force, you are scraping off one sheet on the paper. Yeah? And every time you use your pencil a bit more and you sharpen it every time, you're actually all shaving off sheets of giant structures. Right? That's why you can write with pencil, lead, but not with diamond. Because diamond, no matter how you scrape, the carbon atoms aren't going to come off. Okay, I don't know if it's toxic or not. But you shouldn't be putting that in your body.
So when you are writing with a pencil, you are actually transferring sheets of carbon.
Isn't that cool? Yeah? So every time you write, one sheet is coming off.
Same as all of the atoms are joined by covalent bonds, these materials have very high melting points.
So there's the first property that we take note of. When we look at giant structures, the melting point and boiling point is very, very high. You tend to observe this when the structure is a giant lattice structure. When there are so many covalent bonds or ionic bonds, the melting point and boiling point is very high. Yes? How they make glass? Oh, okay. So how they make glass? They take sand, and really they have to apply very, very high temperatures to melt the sand. Then they allow the sand to cool, and then they rejoin together in a different way that allows it to be transparent. I don't know lah. Oh, I suspect glass probably first appeared, most likely what happens is that volcanic eruption. Then the sand melt, then they observe when the sand cools, it becomes this transparent. Then they apply it. I suspect. Okay? Okay, so that's the first property, high melting and boiling point.
Graphite is very soft. The structure of these materials also determines their electrical conductivity.
So, this is where you need to differentiate a little bit. Second point, not all giant covalent lattice structures are hard. Some are soft. So I'm going to put a hard / soft because it depends on the substance. Then that's why I need to know these two case studies. Because, for example, when you look at diamond is hard. But when you look at graphite is soft. So this one is case by case basis. It's not always the same. But high melting point always the same. It takes a lot of temperature to melt even your graphite or pencil lead. Okay, so this is a point you need to take note of. It's different depending on the substance. Yeah. Okay, then here I'll ask, I didn't quite mention simple molecular structure. Is it hard or soft? We usually don't talk about hard or soft because simple molecular structure tends to not exist as solid state. Because the force of attraction is very weak, it tends to either appear as liquid or gaseous state. So like water, liquid. CO2, gas. H2O2, gas. Because the intermolecular force of attraction is so weak, tends to be gas or liquid state. Yes? Okay. Yes, Z is right. If the covalent substance is arranged in the format of graphite, you can expect it to be soft. But if it's arranged in the format of sand and diamond, then you can expect it to be very hard. Okay, good question.
The structure of these materials also determines their electrical conductivity.
Now here comes the interesting part. Can they conduct electricity? Okay, out of these three structures, only one can conduct electricity. Okay, how do you know?
Because of the odd one out.
Why do you learn this in primary school?
Don't put your pencils to the side with the odd one out.
Oh, yeah, graphite can conduct. Okay, so now at the JC level, you will learn why. Why can they conduct electricity? And you have enough chemistry knowledge to know why now. Okay, let's have a look.
Diamond does not conduct electricity at all because its electrons are locked up in covalent bonds, whereas graphite contains free electrons and so can conduct. Silicon is found in semiconductors, and it's for adding other elements, like doping, that it allows partial conductance, which has applications in computing. Table salt, sodium chloride.
So let me elaborate. Why is it possible for it to conduct electricity? For you to understand this, you require to understand what you've learned before the previous chapters. Here, let's look at diamond. When you look at diamond, every carbon atom is bonded to 4 other carbon atoms around it. So I'll show you an example. I'm going to draw covalent bonds, as what you all have learned. So here I put a dot, cross. I draw another carbon, a dot and a cross. This can go on endlessly. So over here I draw another one, another one, another one. I'm going to stop like that because technically I can continue on and on. These 4 carbons can join more carbons, but I'm going to stop here. You look at this carbon in the middle, it has 1, 2, 3, 4, 5, 6, 7, 8 carbons. It has used up all its electrons. Okay, this is in diamond. In graphite, it's a bit different. In graphite, it says each, okay, look at graphite part B here. Each carbon atom forms covalent bonds with only 3 other carbon atoms. Okay, so let's look at graphite. For graphite, each carbon atom only forms bonds with 3 other carbon atoms. 1, 2, 3. So here I'm going to join 3. Okay. So this is graphite's way of bonding, but there's a problem now. Each carbon actually has how many electrons? 4 electrons circling it. So, if I only use 3 electrons to bond to 3 carbons, I have 1 electron left over, right? This is the reason why graphite can conduct electricity. This electron ends up being free to move along that sheet. So you see, every sheet of carbon, every sheet of graphite, there are spare electrons that can travel along this entire sheet. Okay, that's why it can conduct electricity. I think in your textbook it describes these electrons as delocalized. Can you go to B part 3? Page 64, B part 3. Page 64, B part 3. You read the paragraph. It says each carbon atom only uses 3 of its 4 valence electrons. The 4th valence electron from each carbon atom is, highlight the word delocalized. Delocalized means it is free. Local means you stay put, right? Like, if you look at your local area, you find this and that. So local means in the vicinity. Delocalized means it is free to move. That's why graphite can conduct electricity, because it has spare valence electrons that are free. They are what we call delocalized. So you should find that in your textbook. That's why you can conduct. Okay? And that is where we end off with covalent structures. I'll pause here for a while and I'll summarize, then we'll take up. Oh, it's connected to 4. So look at this carbon atom here, it's connected to 1, 2, 3, 4. Yeah. But this one, if I change the angle a little bit,
So when
so you look at how graphite in your textbook also shows every carbon atom in graphite is bonded to 1, 2, 3 only. Okay? Yes, I said? Oh, yes, you can cut it. Why you must go together? Table, toilet party. Yes. Okay. Okay, quick. I'm going to stand by cargo. Okay, now, there's no difference literally for teams. Like you can literally share device if you want to. Okay, you can work with your friend if you want to. Okay, you can grab your devices if you need to.
Joshua, I trust you.
It's all about this physical
I'm not
structure.
man. I aim at a tree for you. He's tree. And let's play catch up. I throw them higher.
This show is full of possibilities. Okay, the scope of this carbon, I'm going to test the structures of all that we learned. So I want you to be able to know the ionic structures and the covalent structures. This is what we are testing. I'm not testing all the period, group, electronic configuration anymore. I trust that you are quite good at it by now. Okay, once again, nothing insensitive. You just put your own name. Hey, don't curse Su Cheng. Hey, so was Su Cheng joining from class next year? You were feeling
do you get?
Most of the time, simple molecular structures exist as gas or liquid. They rarely exist as solids.
I'm 1 point behind you.
Well then, well done, Kaisen.
Daryl will win like Esther, go away.
Oi, not nice. Oi, he win.
I trust you, Esther.
Trust you.
Pink color, pink color.
Pink color. Pink.
Well done, full marks, huh? This is a class. Baba.
Isaac.
Become king and king.
Sorry. Oh no, what is it?
This is important, huh? Ions, when in solid state, they are all vibrating above each other, like solid. Why do they have high melting points? What's the difference between the first and the answer? No, one of them is correct. Hey, why not molecules? Take note. Hey, hello. Uncle. Okay, first what's the difference between atoms and molecules? Please observe. So when you look at simple molecular, for example, when you look at H2O, the covalent bond here is very strong, but this bond here is weak. Okay? Okay, but when you look at giant covalent, so let's look at a giant version. So let's look at, for example, hey, boys. Okay, when you look at carbon, for example, you look at diamond, they are bonded many to each other, but it is an atom to atom. There is a covalent bond. Okay? So it is not between molecules. Molecules, this is a molecule. And this bond is weak, huh? But between atoms, it is strong. Hey, there should be two answers, right? Hey, okay, sorry. You should have two answers. Covalent bonded substances can have this structure and this structure. So those of you that chose blue, actually you should be correct as well. Okay. Okay, I give you okay, good job. Solid state, huh? Okay, Tristan is well, he's going to become the camp king. Sean can conduct electricity in solid state. Well done. Diamond cannot, diamond cannot. Or still Tristan, huh? Why do I? Yeah, but yo, she was to get wrong one. Okay. Hello. question carefully. Question says, why do ionic compounds have high melting point? Okay, now it shows because they have strong covalent bonds. Yeah, ionic compound won't have covalent bonds, right? Okay. Then next, ionic compound or atoms are ions. Okay, so totally off. Atoms and ions are different. Okay, so Tristan, yeah. Okay, listen. That's a great question. What is the difference between an ion and an atom? So let's look at, for example, ionic compound versus, let's say, diamond. Okay, here I have diamond. Okay, and so on and so forth. Here I have ionic compound. So, what is the difference between ions and atoms? Okay, the difference is. Hey, hello, hello. What's the difference between ions and atoms? Ions versus atoms. Okay, yeah. So ions have a charge. Atoms have no charge. Okay. Ions have a charge, atoms have no charge. Why do simple molecular structure have no melting point? You know why you got it wrong? Okay, so the correct answer is this. It is this force of attraction between the molecules that speak. Okay, next one, last one. Hey, what the? Does anyone have Lucky? Huh? Tristan, you have three devices. Who is Barbie? Who is Barbie? Oh. Why did Rashmika suddenly rise?
Great, guys, believe me. Hey, how much?
Property, but it shows can conduct when molten. That is what. Okay? So careless Who is Barbie? Rashmika is now the camp queen. Well done. I have all three. What? How do you do that? How do you press 3 at once? For this epic camp queen. Hey, the ultimate camp queen. It's quite confused. Okay, because of that, I'm gonna give you the key to my house. I just saw this key on the floor. Doesn't matter, you're still not the king. Okay, we're going to end up today with the last kind of bond. James Bond. Okay, this is the last kind of bond. You erase the whiteboard. Many of you have been asking me, hey, metal and metal, how? Okay, the last part of the chapter. We look at what happens when you have metal and non-metal. We look at what happens when you have non-metal and non-metal. But what if we have metal and metal? It becomes black. Why? Metal is not black. Metal tends to be silver and lustrous. So how? If I have metals, okay? If we have metals, we will form something called metallic bonds. Okay, I'm going to show you that metallic bonds is kind of interesting. It is more similar to ionic bonds than it is to covalent. We will see why.
Metals are used in many everyday objects. This morning, when I woke up, I decided to have a soft-boiled egg and a cup of coffee. The pot I used is made of metal. The kettle is made of plastic, but the coiled heating element inside it is made of metal. Metals are good conductors of heat. This is the reason why metals are used to make these everyday objects. You would never see a pot made of wood or a heating element made of plastic. Metals are also good conductors of electricity. The wire connecting your kettle to the electrical socket is actually made of many copper wires, insulated with a layer of rubber. Think about the shapes of the everyday objects we described. The pot, the heating element inside the kettle, and the copper wires. Notice that they are very different. Metals are malleable. This means that they can be molded into different shapes. Metals are very ductile. This means that they can be stretched into wires. To fully understand these properties of metals, we must understand metallic bonding. When we talk about metallic bonding, we are actually describing the electrostatic attraction between the metal ions arranged in a lattice structure and the free-floating electrons around them. Since these electrons are free to move around, the term sea of electrons is also used. What is a lattice structure? And where have you heard this term before? Let's pause the lesson to think about this and resume when you are done.
So where else have you heard? Okay, in covalent as well as in ionic. So actually we call this structure a giant. You may educated guess up. Giant metallic lattice structure. Okay? The only time you will use simple molecular is if you find that they exist as molecules by themselves. Okay?
Repeating pattern. The term lattice structure means that there is a regular repeating pattern. We have heard this term before when discussing ionic lattices. It is used to describe the alternating positions of the metal and non-metal ions. In metallic structures, however, there are only metal ions. These metal ions are arranged side by side in a regular repeating pattern. The free-floating electrons act like a glue and hold the structure in place. This is a very strong attraction and explains why metals have high melting and boiling points. A lot of heat energy is needed to overcome this attraction. This is also why metals are very good conductors of heat. Free-floating electrons are the reason why metals can conduct
strong electrostatic attraction will remain, and therefore the structure stays intact. Let's think about it. Cars and bicycles, trains, planes, buildings, cutlery, spectacles, furniture, and endless items can be made from metals. To recap, the electrostatic attraction between metal ions arranged in a lattice structure and free-floating electrons is known as metallic bonding. This explains many properties of metals. They are good conductors of heat and electricity, have high melting and boiling points, and are malleable and ductile.
Okay, so some terms I would like you to take note of. That you can find your textbook. Please open your textbook on page 65. Please open your textbook on page 65. Samuel, please open your textbook to page 65. Okay, so please highlight the word, the first paragraph, C of delocalized electrons. Please highlight that, C of delocalized electrons. Can you see the word? So this is what I want you to highlight. C of delocalized electrons. C of delocalized electrons. When else did I use the word delocalized? In graphite. Remember graphite, the sheets, we have electrons, they are free moving. That's what delocalized means. But in metals, it's quite extreme. Every single one of these metal atoms will give up an electron. So here I'm going to give up electron because then becomes positive cation. Another electron free. Another electron free. Okay, and so on and so forth. If every single metal atom gives up its electron, we end up getting like a sea of electron strands encapsulating all of the metal cations, kind of like a netting. Okay? But it is this sea of electrons and the cations that end up attracting each other quite strongly. And that's why their metals have very high melting point. The electrons and the cations attract kind of like a netting, attracting all the cations together, and the bond is actually very, very strong. Isaac? Oh, okay, if 8 of them goes to? Oh, okay, but you see, metals prefer to lose electrons because they have very few valence electrons, right? They prefer to just lose and they have a full shell. So they would not want to gain any. So you will not find electrons going to another metal atom. But if you go and break a non-metal nearby a metal, you may end up giving the electrons over. Okay? So this explains why metals also have a classic property of all lattice structures. The melting point and the bonding point also very high because the metallic bond is very strong. Other than that, we learned before in our previous chapters that metals also are malleable or ductile. Malleable means can change shape. Many of you have metal objects, right? You have dents here and there, like your bottles or your iPad, right? Lots of dents. Metals can change their shape because actually, if I were to accidentally apply force downwards over here, and all of these metal ions end up shifting a little bit down, it's fine because I still have this sea of electrons, like a netting, holding all the cations together. That's why metals can change its shape so freely with a little bit of force applied, but it can retain its shape. But for ionic compounds, it's different. If you look at ionic compounds, they are oppositely charged and they do not have this sea of electrons. So if you were to apply a force downwards here and everything shifts down by 1, plus, minus, plus, they end up repelling each other now and end up fracturing and breaking off. There's no sea of electrons holding everything together like a net. But for metals, you apply force, it will not crumble. It will still hold together because of this sea of electrons. That's the beauty of metals. Metals, as we know it, also conducts electricity. And we learned that as long as there are free mobile charge carriers, can conduct already. In this case, we have a lot of free electrons. So all of these electrons here, that's my red marker. All of the electrons are free to move. These electrons can help to conduct electricity. They are free to move. Okay? So these are some of the physical properties of metals. Can metals form compounds? Meaning if I take two metals and put them together, do they form compounds? No. Okay? So if I were to take, let's say, copper and I mix with zinc, you will not get a metal compound. All you get is a mixture of metal cations. You may have learned in primary school before, have you learned the word alloy? Okay? So let's say that this cation here is copper. If I were to add zinc in, this is what you end up looking like. Right now, if I were to add zinc in, you may end up seeing this. So 1 times big zinc. Okay? Maybe another big zinc over here. I'm trying to make it a bit different in size. While there's still a lot of copper ions still beside it. But the big one, I'm trying to represent zinc. But you may have heard before that alloys are much stronger than the original metal. Like steel. Steel is really, really strong. They cannot bend that easily. Why so? Because if you have metal ions that are different shape, different size, now it's not so easy for it to change shape. For example, if I were to try to press down over here now, this particular metal ion is in this way. It cannot just shift as easily as before. Previously everything was arranged in a nice row and columns. Press down, you can just easily move down. But now with all these different size metal ions, it kind of disrupts the flow. If I were to press down over here, it's disrupted by this big ion here. It cannot now bend as easily. So having different kinds of metal ions present makes it harder usually. But this is not a compound, it's just a mixture of cations. Okay? So metals cannot form compounds. Okay, I'm going to pause here. Then again, everyone, you can have a look at page 65 and page 66. Page 65 and 66 is where we have just covered. Then again, you do a little bit of silent reading and do a little bit of highlighting. Page 65 and page 66 is what we just covered. The remaining time, just do a quick silent reading. Read through the points.